we can use curl to talk about the conservative vector criterion in 3 dimensions. And remember, a conservative vector field is one that can be written as the gradient of some function, f, where f is a function of x, y, and z in this case. So we're now in 3 dimensions. And let's go back up here and look at the definition of curl. So it was the del operator cross product with the vector field, but then if we actually wrote it out, we could get something like this, which if we wrote it without all that partial notation and just use the subscript notation, we can write ry minus qz, comma, I'm going to reverse this order, so I can write pz minus rx, comma, qx minus py. And this looks a little bit like the conservative vector field criterion for 2 dimensions, right? In 2D, conservative vector field, it was very much related to qx minus py equals 0, and there were some other conditions about the region and the vector field being nice. Okay, well now we've got 3 things. Okay, and this last one is actually the same. So we can write the conservative vector field criterion for 3 dimensions. So let's say f has components, this is part of it being nice, that have continuous partial derivatives. So if you took the partial derivatives, everything would be nice. Then we can write 2 statements. First of all, if f is conservative, then the curl of f has to be the 0 vector. So all the components. The last component came from the 2-dimensional vector field, but now it's got to be true of all the components. So curl of f is 0. And then the second one is if we have f, there could be more complicated ways to say this, and we could define the notion of simply connected in 3 dimensions. But for simplicity, we're just going to write f is defined on all of R3. This replaces simply connected, basically. It's a little bit stronger, but that's okay. So if f is defined on all of R3 and the curl of f is the 0 vector, then f is conservative. And then one particular consequence of this, because f is conservative means f has to be the gradient of some function. So that, like a consequence of the first one, would be that the curl of the gradient of some function is always the 0 vector. Take any function, take the gradient, take the curl of that. It's got to be 0. So that's cool.